What are IVT, MVT, and Rolle's theorems? Well, let's start with IVT, which stands for Intermediate Value Theorem. The core concept goes as follows. Let's say we have a function that is continuous for all values in its domain. Now let's look at that function specifically in the closed interval between the arbitrarily chosen a and b. IVT then goes as follows. Considering that f of a and f of b aren't equal, if we were to come up with a value c that was between f of a and f of b, then there is a value between a and b that we could plug into f to get c. Basically, it's like saying you know where a laser beam starts and ends, and you also know that there is a pane of glass in between those 2 points. Using this knowledge, you can conclude that the laser beam crosses the glass at some point between its start and end. Now, if you're hearing this for the first time, a certain phrase involving Sherlock Holmes might come to mind, as IVT seems simple towards the point of redundancy. But it is required in calculus as a way in which to prove certain statements. For example, what if that glass pane of ours was the x-axis, and we were asked to prove whether a zero exists on a closed interval of a rather unwieldy function. An example of this would be g of x is equal to e times x to the power of 2 minus pi, and the question was whether the function has a zero between x equals 0 and x equals 5. Now, you could of course set the function as equal to 0 and then limit your answers to the domain, which would also give you the x value that the zero occurs at. The thing is, though, the question isn't asking us to find the zero, it's asking us to prove that it exists. So, we could use IVT to our advantage here. Instead of having to solve out the equation, we can just show that it is continuous between x equals 5 and x equals 0, and then see if we can find both positive and negative values for g of x within that domain range. We will effectively be saying that since g of x exists in the domain on both sides of the x-axis, then it must have passed through the x-axis at some point in the given domain. For this, we will start as broad as possible with the values defined in the domain, testing the function at g0 and g5. Sure enough, g0 is negative and g5 is positive, meaning that through IVT we can prove that the function crosses the x-axis and thus has a zero between x equals 0 and x equals 5. Now on to mean value theorem, or MVT. To explain this, I'll go back to f of x, which is again continuous in the closed interval between x equals a and x equals b. Something else that needs to be true for MVT to apply is that the function is differentiable in the open interval between a and b. The first thing we are going to do is find f of x's average rate of change between the points a and b, or in other terms, the slope of the secant line that runs through both a f of a and b f of b. We can write this as f of b minus f of a over b minus a, the average rate of change, which we will call r. In a nutshell, MVT states that there is a value c in between a and b, where the derivative of the function at that point, or the slope of the tangent line that intersects the point, is equal to r, the average rate of change between a and b. Let's now consider a slightly different scenario with a new function, h of x. As with before, we'll take a look at the interval a, b, where the function is both continuous and differentiable. Now though, h of a is equal to h of b. So then, what happens if we were to apply MVT here? Well, h's rate of change between a and b would be 0 as there is no rise, only run, meaning that the slope of the secant line connecting them is equal to 0. This means that there must be a point in the function between a and b with a flat tangent line, or a derivative of 0. Interestingly enough, this is itself known as another theorem, Rolle's theorem, which again only applies in cases where the function's value at the beginning of the interval is equal to the value at its end, making the average rate of change between the 2 points 0. Now, to wrap things up, I'd like to go through an example. prove that the function p of x, which is equal to 2x to the power of 5 plus 3x to the power of 3 plus x minus 3 has only one real zero. Well, the first thing we should do is to prove the function has a zero to begin with, which we can do with IVT. Remember, in any case where you are being asked to prove the existence of a zero, but not the actual value of the zero itself, your gut instincts should be to apply IVT. P of x has no discontinuities, making it a continuous function, meaning that all we would have to do is find one point where the output of the function is negative and another where the output is positive, to prove that it does cross the x-axis at least once. For this we can use p of 0, which is negative 3, and p of 1, which is 1. So then, since the function is continuous and has both positive and negative values, it has to pass through the x-axis at least once according to IVT, and therefore has at least one zero. Now on to proving that it only has that one. Considering that the function is both differentiable and continuous at all points, we can apply MVT, and more specifically Rolle's theorem. Going backwards from its definition, if f of a is equal to f of b, then there has to be a point in between a and b where the derivative of the function is 0. So then, for there to be two or more zeros, there has to be a point in between them where the derivative of the function is 0. If the derivative of the function can never be 0, then according to Rolle's, it is impossible for that function to have more than one zero. So then, let's find the derivative of p of x, which we can do by employing power and sum rules. This comes out to be 10x to the power of 4 plus 9x to the power of 2 plus 1. We can now see that the lowest possible value for the derivative of p of x is 1. Now remember what I said before. For there to be more than one zero, there has to be a point in between the zeros where the derivative or slope of the tangent line is itself 0. Considering that in this case the derivative can never be anything lower than 1, we can conclude that it is impossible for the function to have more than one zero. So, we know from applying IVT that the function has to have at least one zero, and from applying Rolle's theorem that it can have no more than one zero, leading us to the conclusion that it must have one and only one zero, thus proving the statement.